Our next thoughts were given by Sasaki Das, and the topic is Are we learning the right features? A framework for evaluating deep learning-based software vulnerability detection solution. Go ahead, Sasaki. All right.
Thank you, everyone. I'm Shaktavi Das. I'm a PhD candidate at USC, and I published this paper with my lab mates Shosoyo Tasnim Fabiha and Saad Shafiq and my thesis advisor, Professor Nenad Medvedovich. Let's first talk about what deep learning-based software vulnerability detection is. So we have a sample of a vulnerable code here, and this is a vulnerable code because in line 3, we are trying to we allocate 10 bytes to a buffer data. And then in line 5, we're trying to write 40 bytes into that data. And when you do that, it causes a buffer overflow. And the task is to detect the presence of such code using deep neural networks. Now, this detection can come in many granularities, depending on your implementations. Some of them detect them at the function level. For example, we have SVD, which was published in 2023. There's SIFT. Some of them detect them at the slice level, like Deep Wukong and Xavier, and then some of them detected at the line level, like LineVol and LineVD. Unfortunately, there are studies that show that when you try to use these detectors on other datasets, their performance drops significantly. And that prompted us to ask, how reliable are these detectors? In the sense that how do their predictions change with respect to the change in input? For example, if there's a significant change in input, do they alter their predictions? If there's a very trivial change in the input, do they still retain their predictions? And can we somehow use these changes in input to come up with a way to evaluate them? And in this paper, we tried to answer these questions by coming up with ways to understanding these code properties that contribute to their predictions and use that understanding to build a perturbation-based framework that can help us evaluate them. So to understand these code properties, in this paper, we propose a three-pronged approach. First, we want to identify the properties that actually contribute to vulnerabilities. We call them vulnerability features, or VFs for short. Next, we also want to look at the properties that only falsely correlate with vulnerabilities. We call them spurious features, or SFs. And lastly, we want to see how these vulnerability features and spurious features impact these detectors. Now, to get a quick overview, we first analyze the existing vulnerability datasets, and based on our analysis, we list the most commonly occurring vulnerability features. Spurious features in the context of vulnerability detection have been studied before, so we analyze the existing studied spurious features, and with our vulnerability features, we form a taxonomy of code features for the context of vulnerability detection. And then we use this taxonomy to build our perturbation-based framework, which is Viper, whose job is to analyze the impact of the vulnerability features and spurious features. Now let's take a look at each individual module of our approach, starting with how we analyze the vulnerability datasets. So to identify the vulnerability features, we analyze the SART dataset, and the biggest reason we chose this dataset is because this is the only one that gave us annotations that describe the vulnerability. Now, these annotations look something like this. This is the exact same code we saw earlier, but this is how it appears in the dataset. And if you see, you'll see that there are strategic comments in the sample that has prefixes like flaw, potential flaw, that tell you where the vulnerabilities are and how they contribute. The corresponding fix for the vulnerability will have a prefix like fix that tell you how you can fix it. And what we wanted to do is we wanted to encode or capture this description so we can analyze them. And to do that, we used a structure called the code property graph. And if you extract the code property graph of this sample, you get a graph that looks like this. And the way you want to read this graph is each node is associated with a line number and a bunch of key value pairs that give you different metadata about the statement in the line number. Now, full disclosure, this is not the entire code property graph of the sample. It has a lot more nodes and a lot of different edges as well. But for this illustration, we're only showing the data dependence edges. And the thing about data dependence edges is that it also comes with one key value pair that tell you which variable is associated with the data dependence. Now you'll see that the description on the left side is actually captured by this red edge in the graph that tell you what the vulnerabilities are. So using these, we encoded the top 10 vulnerabilities features of the dataset. And then when listing them, what we wanted to do is we wanted to capture an is-a relationship between them. And that is because if we could somehow do that, that would mean on top of getting individual insights for the vulnerability features, we'll also be able to get a more aggregated view of the insights as well. So with that in mind, we grouped the first 4 under overflow vulnerabilities, the next 2 under deallocated buffer use, the next 2 under numeric range, and the last 2 under sensitive API. Now, for the spurious features, like I mentioned before, they have been studied before. So what we did is we categorized them into 2 different categories. The first is the ones that affect the token representation of code, and the other ones are the ones that affect the graph representation of code. More details about the difference between these 2 types are provided in the paper, but for the interest of time, we'll just show you how it falls under the taxonomy. So we have our vulnerability features, and we also have our spurious features, and we put them all under the category umbrella of code features, and this is our taxonomy for vulnerability detection. It's important to note that this taxonomy is not a comprehensive one, and it's open for extension in the future. We just use it as an illustration to see how we can apply it for Viper. So next, let's talk about our perturbation-based framework, Viper. So Viper has 3 components. The first is a feature detection component, the second is a targeted perturbation component, and the third one is a solution evaluation component. So to get a quick look at the pipeline of Viper, you have a sample like this, the same sample that we saw before. The feature detection component will look for vulnerability features in the sample, and if it finds any of them, then it will annotate the sample to denote that. And then the annotated sample gets fed into the targeted perturbation component, which generates 2 types of perturbations. We'll talk more about what these 2 types of perturbations are very soon. And then these perturbations and the sample get fed to a deep learning-based detector, which gives us its predictions, and then we calculate the impact of the vulnerability features and spurious features. Now let's look at how each of these components work, starting with how feature detection works. So we have the 10 vulnerability features from the taxonomy. What we do for feature detection is we develop 10 corresponding detection algorithms for each of the vulnerability features. And then for each sample, we extract their CPGs and using Jorn, and then we apply all of our detection algorithms. And if any of them return true, then we annotate the sample accordingly. It's worth noting that for spurious features, we do not perform feature detection because these features are inherent properties of every sample. So now that we have our annotated sample, we generate perturbations. Like we mentioned before, for vulnerability features, we generate 2 types of perturbations. The first is a feature-preserving perturbation. This is the trivial change we mentioned at the start of our talk. And what it does not remove the detected vulnerability feature, and therefore it does not alter the vulnerability ground truth. So it looks something like this, as you can see. We're just changing the size of the data to be 10 minus 1, which does nothing to fix the vulnerability. The other one is the significant change we mentioned earlier, which is the feature eliminating perturbation, or FEP. And this one removes the detected vulnerability feature, and thereby it alters the vulnerability ground truth. So it looks something like this. As you can see, we're just changing the size of the buffer data to match the size that's being used in line 5, effectively fixing the vulnerability. For spurious features, there are some things to keep in mind. Since these are properties of all samples, you want to make sure that these perturbations apply to all samples. And because they're spurious features, they can never alter the vulnerability ground truth, and therefore there will always be feature-preserving perturbations. So the perturbation for the node set spurious feature looks something like this. We just add an empty printf statement. And for the edge set one looks something like this, where we just add an unsatisfiable condition at the start. Next, let's look at how we use Viper's perturbations to evaluate the detectors. So for this paper, we chose 3 graph-based detectors and 2 token-based detectors. And the research questions we wanted to answer was, how do these perturbations affect their precision and recall? what are the satisfaction rates for the perturbations, and by satisfaction rates, I mean how many percentage of perturbations generate a satisfactory response, where a satisfactory response is if you have a feature preserving perturbation, they retain their prediction, and if it's a feature eliminating perturbation, then they alter their prediction. And lastly, we wanted to see how the FPPs and FEPs individually influence the detector's predictions. To answer, we noticed for RQ1, we noticed significant drops in both precision and recall. I will not go over all the numbers here, but for precision, we saw somewhere from 24% to 78% drop, and for recall, we saw over 50% drop in many cases. To calculate the satisfaction rates, we drew this heat map, and the way you want to read this heat map is the darker the color of your cell, the better the satisfaction rate. And if you take a look, you'll see RA and WA, which is the sensitive API call vulnerability features. They're the ones that have the lightest shade of maroon, which means these are the features that the detectors struggle the most with. And lastly, we wanted to look at how the FPPs and the FEPs individually impact the detectors. And how you want to read it is, if you have a high satisfaction rate for FEPs, that means your precision is more stable, which means even if you miss some vulnerabilities in your data set, if you predict a vulnerability, it's likely going to be true. Conversely, if you have a high satisfaction rate for FPPs, that means you have a better recall retention, which means you're likely to catch vulnerabilities if they exist, even if you give some false positives. So based on these two numbers, we categorized our 5 detectors into one of 4 quadrants. And you read it the same way as you did before. The darker the color of your quadrant, the better the result. And what you want your detector to fall into the high category and avoid the low category at all cost. But in this study, we found that in all but one cases, all 5 of them fall under the HL category, which means they have better recall retention, but they have very poor precision retention. So to conclude, in this paper, we find that roughly 2% of all the FPPs change predictions across the board. Roughly 84% of the FPPs retain the predictions, which is unfortunate. And for graph-based detectors, we notice a precision recall drop of up to 29% for spurious features. And for future work, what we want to do is we want to incorporate these vulnerability features in training, also while negating the spurious features in training. And with that, I'll leave for questions.
Time for question.
Thank you for the interesting presentation. I have a question on the perturbation. I want to wonder, how did you do the perturbation? Like, is it automatically generated or is manual? And sorry?
No, go ahead.
And then because the follow-up question after that is that if it is automatically generated, then how do you make sure, how do you know that they are really removing the vulnerability feature, or they are not removing the vulnerability feature by chance? So that's the question. Thank you.
Yeah, so that's a good question. So it is to answer the first part of your question, it is automatically generated. So what we did to confirm that is we manually analyzed all our perturbations. And we can say, based on our analysis, with 95% confidence and a 5% margin of error, that they do change the vulnerability ground truth in cases. Yeah. Yes.
Maybe a clarification question, because I'm not an expert in this, but I'm just wondering how the results that you got there can help us to make safer code or with less vulnerabilities. Could you just...
Yeah, that's a good question. So I'm just going to go back to one slide before. So the way you want to use this result specifically, so if you have to choose between one of the detectors and you want to choose which one is best for you, you can see which quadrant your detector falls into, and based on that, you can decide. For example, if your detector falls into the high category, you should definitely use that for your system to analyze vulnerabilities. If it falls into the high-low category, it means you may get false positives, but if there are vulnerabilities in your systems, the detector will catch it. And if it falls into the low-high category, Well, it might miss some vulnerabilities, but if it catches a vulnerability, it's likely going to be true. So you can use that information. If you have a stable system where you don't want false positives, you can use that one detector as well.
Okay, thank you for your presentation. So I was wondering, have you considered in your framework, do you have any notion of the degree of perturbations? I mean, the perturbation can be more applied or less applied. You can so is there any?
Unfortunately, we didn't consider degrees. It's like applied or not applied.
Okay.
It's just that.
The next talk is the online presentation with the video. Will be